Hey everybody, it's Wednesday, February 10th, and as you can see here in the aim today, our goal for today's video is to talk about collisions. Now, collisions are an extremely important topic in this course, something that will come up on the AP exam a ton. And so, because collisions are governed by conservation of momentum, which we covered yesterday for the first time, I want to take a brief moment to just talk about conservation of momentum a little more, sort of review some of the things we talked about in yesterday's video with yesterday's problem, particularly the problem at the end of the video, and then move on into the main topic for today. So it's important to realize here that conservation of momentum is one of the most important topics we will discuss in this course this year. It is extremely important because it is one of the foundational laws of physics that governs almost every interaction. And so we talk about momentum because it is related to force, right? Force is equal to the time rate of change of momentum, as we said. And yeah, it's a measurement of how hard it is to stop an object, we can say. But the most important thing about momentum is that momentum is a physical quantity which is conserved. And as we said yesterday, the most concise way to state the law of conservation of momentum is in the absence of an external force, the total momentum present in the system before the interaction. Now, the interaction here is mostly just going to be one object exerting a force on another object. The total momentum present in the system before the interaction is equal to the total momentum present in the system after the interaction. That's the key idea here. So whatever amount of momentum you have in the beginning, that's the amount of momentum you have in the end. Now, in some scenarios, that law is easier to apply than in other scenarios, as I think you'll see here in a little bit, but that's the idea. And so yesterday, we started with our many days of trying to apply this idea with applying the idea to a problem that we traditionally refer to as an explosion problem. And the first example of an explosion problem that we looked at yesterday was this problem where we had a man in a boat throwing an object, a package, as it said here in this problem. Now, the reason why we refer to these problems as explosion problems is because the objects start together and then push off of each other and move apart in different directions. That's generally the main scheme for an explosion problem. What makes an explosion problem is that the objects start together and move apart. Now, most of the time, you'll see in an explosion problem, the objects start from rest. They don't always, and you'll see some examples of those on homeworks later on. But generally, the objects start together and then move apart. And so yesterday, we went ahead and solved this problem here. And this was the solution. We solved this yesterday, so there's not a whole lot to say. We saw the objects started at rest. The lighter object, the package, was thrown at 4.5 meters per second, and we went through and solved for the velocity that would be gained by the man in the boat, and we got negative 0.34 meters per second. And the key point that I want to make here is that everything that conservation of momentum says conceptually agrees with what Newton's laws of motion say. But the key difference is that conservation of momentum gives you a problem-solving framework to be able to solve for different information. Specifically, conservation of momentum allows you to solve for velocities directly, whereas Newton's laws of motion would only allow you to solve for accelerations. So let's just take a brief moment to think about what Newton's laws of motion say about this problem. If we take all of Newton's laws in reverse, Newton's third law of motion says these objects exert equal and opposite forces on each other. The force that the man exerts on the package is equal to the force that the package exerts on the man. Newton's first and second laws, remember, they really are the same thing, just stated a slightly different way. They dictate how the objects will move as a result of the action of that force. The package, notice here with a tiny mass of 15 kilograms, should experience a larger acceleration because the package has less mass, so it has less inertia, and that means it has less resistance to acceleration. Of course, Newton's second law says the acceleration is inversely proportional to the mass, so with the smaller mass, we should get a larger acceleration. And of course, that's what we see because this object has a velocity change with a magnitude of 4.5 meters per second because the velocity goes from 0 to 4.5. On the other hand, the man in the boat with a mass of 200 kilograms only experiences a velocity change with a magnitude of 0.34 meters per second. The velocity goes from 0 to negative 0.34. So the magnitude of the velocity only changes by 0.34 meters per second. That makes sense. That object, the man in the boat, together, they have more mass, so they have more inertia, which means more resistance to acceleration, which means they should end up accelerating less in that amount of time. And since it's the same amount of time that that force is acting, we end up seeing a smaller speed change in that amount of time because the acceleration is less. And that's really it. Now, something else that we talked about yesterday, but we didn't really get into with this particular problem, and so I think it's important to do that, is that the reason why momentum is conserved is because of Newton's third law. Newton's third law says the forces are equal and opposite. And going through our derivations of equations, we saw that impulse, or the change in momentum, is the product of the force and time. And so since the forces are the same and the times are the same, the impulses are the same, but of course the forces aren't the same. They're equal and opposite. So the impulses are equal and opposite. And the reason why momentum is conserved is because if you're starting with a set amount of momentum and each object has its momentum changed by the exact amount, but in opposite directions, that means the changes in momentum will ultimately cancel. If one object gains 5 and the other loses 5, then the total still stays the same. And that's the key detail. Notice that is exactly shown here in these few lines of the conservation of momentum problem solving. We said here these objects start off with 0 momentum. That usually is confusing to people because they think, well, if it starts off with 0 momentum, that means it ends with 0 final momentum. And doesn't that just mean the objects are not moving? It doesn't. The objects start with 0 momentum, they end with 0 final momentum, but that's together as a system. What this line shows is that the objects finish with momenta that are equal and opposite. And that's because they experience equal and opposite impulses. They started with 0 momentum together. They finish with 0 momentum together, and that just means they have momenta at the end, which cancel each other out. And that's because they had impulses that were equal and opposite, and we can demonstrate that with basic calculations. Since the forces are equal and opposite, and they act for equal amounts of time, the impulses are equal and opposite. So let's take a look at the impulse calculation for the package. The mass was 4.5 kilograms, the initial velocity was 0 meters per second, and the final velocity was 15 meters per second. And so the impulse, which is the change in momentum, we can calculate by using the equation m times the change in velocity, because if momentum is mv, then the change in momentum is m times delta v. And so we take its mass, 4.5 kilograms, and we multiply it by the change in velocity, which is 15 meters per second minus 0 meters per second. We end up getting an impulse, or change in momentum, of 67.5 kilogram meters per second, or to two significant figures, 68 kilogram meters per second. Of course, if we do the calculation for the boat, we're going to have different numbers. We have a much heavier mass and a much smaller change in velocity. But notice here, using the exact same setup, just with the data for the boat, we get the mass times the change in velocity, giving us 200 kilograms, a much bigger mass, times negative 0.34 meters per second minus 0 meters per second, so a much smaller change in velocity. But notice, it still gives us 68 kilogram meters per second. It, of course, is just negative because the impulses are equal and opposite. And that's the key detail. You've probably heard me say a lot this year that when you sit down for that AP test, the last thing I'm going to say to you is, remember, go back to basics. And that's what I mean here in these problems. Going back to basics means applying the basic concepts, and that's what you need to do here. The forces are equal and opposite, the impulses are equal and opposite, and the momentum is conserved. The rest of this is just seeing how that plays out mathematically. Now, as we mentioned, momentum is conserved in any situation where the objects are exerting equal and opposite forces on each other, which is always true, and there's no external net force. And so that applies in a lot of situations in which the objects are traveling and then smash into each other, or in other words, in collisions. And that's really what we're going to spend the bulk of this unit talking about. Take a second to pause this video here and write that down. If you want to, you will end up doing a ton of these calculations or similar calculations on your own, so you may want a sample of one in your notes. And when you hit play, we'll start to talk about collisions. So in this course, we're going to apply conservation of momentum to a variety of problems, but in particular, we're going to apply conservation of momentum to collisions. And in this course, we apply conservation of momentum to 3 types of collisions. The first kind is called a perfectly elastic collision. The second kind is called a perfectly inelastic collision. And the third kind is just called an inelastic collision. And I don't really want to overwhelm you with definitions right now, and so we'll just take these one by one. And so we're going to start for today by talking about what I think will ultimately, at the end of this, be universally agreed upon is the most difficult one to solve. And that would be a perfectly elastic collision. This probably would be a smart thing to write down, though. So take a second to pause this video here and write that down. And when you hit play, we'll move on. Let's start out by defining a perfectly elastic collision. A perfectly elastic collision is defined as a collision in which both the kinetic energy and the momentum are conserved. That is unbelievably important. Both the kinetic energy and the momentum are conserved. And so this is not all that difficult to understand, but just to get the point home, if the momentum is conserved, that can happen in a variety of situations. It's only a perfectly elastic collision if both the kinetic energy and the momentum are conserved. So there's going to be no external force changing the momentum, and there's going to be no external work changing the kinetic energy of the objects. That's very important. Now, of course, because both the kinetic energy and the momentum are conserved, that means the relevant equations are going to be conservation of momentum, m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime, your standard conservation of momentum equation, and conservation of kinetic energy, 1/2 m1v1 squared plus 1/2 m2v2 squared, that should say, plus 1/2 m1v1 prime squared plus 1/2 m2v2 prime squared. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, big note here. Since a perfectly elastic collision is a collision in which both the momentum and the kinetic energy are conserved, essentially, this problem is a system of equations problem, where both equations must be solved simultaneously. This is unbelievably important. This is the governing principle for the entire problem. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So the main idea is, to some degree, this is not new. Because, remember the Atwood's machine problem? That's a system of equations problem. We had multiple equations and we had to solve them simultaneously. Of course, in this situation, the 2 equations that we have to solve simultaneously are these 2. And so it should go without saying, this is a nightmare. These equations are big, they're long, they're disgusting. This is a mess. And so what we're going to do, because we're smart and we know math, is we're going to rework the equation for conservation of kinetic energy to get it into a form that is a bit more manageable. Because think about how you would do this. Let's just go back here for a second. These equations can't really be added together because that doesn't help you, right? If you think about the Atwood's machine, the reason why we add the equations is because the tension is positive in one equation and negative in the other equation, and then they cancel. But because all the velocities in the kinetic energy equation are being squared, even if something was negative, when you square it, it's going to become positive, so that like doesn't help. What you would have to do is solve this by substitution. So like think about solving the top equation. Like let's just take the conservation of momentum equation and solve it for V1. You would get m1 v1 prime plus m2 v2 prime minus m2 v2 divided by m1 if you solved it for v1. Then you would have to come down here and plug that into this equation. It's squared. You have a 3-term equation now for v1 that you have to square and then distribute the m1 to, and a half, and then with all the, it's a nightmare. But because we know math, we can do a little reworking of the equation to get it into a form that is much more manageable. And so hopefully you appreciate the math we're about to do here, because to some degree, it's a lifesaver when it comes to solving these problems. And so the first thing we're going to do here is we're just going to start by writing down the equation. m1 v1 squared, 1 half m1 v1 squared plus 1 half m2 v2 squared equals 1 half m1 v1 prime squared plus 1 half m2 v2 prime squared. It's even annoying to write down, let alone solve this whole thing. So hopefully you appreciate the step that we're going to do. Now, what I want to do first is I just want to gather the 1s and 2s on the same side of the equation. And so I'm going to kind of go a little extra with just like showing all the steps here, because I really do want you to follow this. And so we're going to take 1 half m1 v1 prime squared. We're going to subtract that from both sides. And then we're going to subtract 1 half m2 v2 squared. And so when we do that, we're just going to end up with 1 half m1 v1 squared minus the prime term. So 1 half m1 v1 prime squared. And then we're going to set that equal to, notice this is a positive one, so 1 half m2 v2 prime squared minus, and then just 1 half m2 v2 squared. So now we've gathered the 1s and 2s. And so I want you to think for a second, why am I gathering 1s and 2s? Well, it's pretty clear, I think. We're gathering 1s and 2s because now, notice, both terms on this side of the equation have an m1, and both terms on this side of the equation have an m2. And before I even factor anything out, it's important to realize also that every term in this equation has a 1 half. So let's just get rid of that right away too. The half cancels because it's in every term. Now both of the terms on the left-hand side have an m1. So I'm going to write m1, and then I have v1 squared minus v1 prime squared. And on the right side, I have m2 in both terms, and so I'm going to have v2 prime squared minus v2 squared. Okay, so that's correct. Now, I've got a much neater little equation, but like, does this really help me? Not really. But we can do a little nice trick here at this step to greatly simplify the equation. Now, I want to be clear about what we're saying here, because the goal of this is simplifying the equation. What we are about to do right now is make the equation worse. Ultimately, though, we need to do this in order to make the equation better. We first need to make a mess before we can clean it up. The mess that we are going to make here is in recognizing that what I have is v1 squared minus v1 prime squared. Something squared minus something else squared. Or, in other words, the difference of two squares. Remember, a squared minus b squared equals a plus b times a minus b, right? That's difference in two squares. So what we really have here is that v1 squared minus v1 prime squared is v1 minus v prime times v1 plus v prime. I personally even think that's better and more manageable to work with, just because you don't have to square anything anymore. So we're going to get rid of those squares. And so what we're going to end up with is m1 times v1 minus v1 prime times v1 plus v1 prime. And then that's equal to, and we can do the same thing over here, because this is difference of two squares over here too. So we have m2 times v2 prime minus v2. Of course, now the prime is first, so we have to be a little careful with that step. And then v2 plus v2 prime. The order doesn't really matter on the addition. Now, I'm going to switch the slide here, so if you want to finish writing some of this down here, take a second to pause this video and write that down. And when you hit play, we'll continue on with this work. We're almost there. I've just rewritten that last line on the top of this slide so we can just move on. Now, whether you realize it or not, this is a really important step because you now have something really, really, really important in there. And what you have in there that's really important comes from momentum conservation. What conservation of momentum tells us is that m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime, right? And so if we do the exact same thing, if we gather all the ones and twos on one side of the equation, we have m1v1 minus m1v1 prime equals m2v2 prime minus m2v2. Same thing, just reshuffled the equation to gather the terms. And when I factor out here, I have m1 times v1 minus v1 prime equals m2 times v2 prime minus v2. And now this is the key realization that you need to have. m1 times the difference in these velocities, v1 minus v1 prime, is the same thing as m2 times v2 prime minus v2. Why am I bringing that up? Look here, m1 times v1 minus v1 prime. That's that exact term. And then over here, m2 times v2 prime minus v2. Those are the same things. And what happens when we have the same things is that they cancel. And so I'm just going to go ahead and rewrite that one more time so we can just show it. m1 times v1 minus v1 prime, and then we have to multiply it also by v1 plus v1 prime, equals m2 times v2 prime minus v2, and then plus v2 plus v2 prime over here. And so what we're saying here is that that is equal to that, so they cancel. And what that leaves us with, believe it or not, from that whole big disgusting thing, 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared is v1 plus v1 prime equals v2 plus v2 prime. And if you don't think that's cool, then I feel sorry for you. Because that is extremely useful now. Instead of having to solve that big disgusting mess, this is what we have to solve. Now, we can even do one better. Because notice now what we have is the ones gathered on the same side of the equation as the twos. But that's not what the conservation of momentum equation traditionally looks like. We don't gather ones and twos. We take initial and then on one side and final on the other side. And that's what we're going to do here now too. And when we do that, we're going to have v1 minus v2. And then on the other side, we'll have v2 prime minus v1 prime. And we're actually going to go ahead and write that like this, just so the order is the same. v1 minus v2 equals the negative of v1 prime minus v2 prime. And that is an extremely useful equation. The reason why it's an extremely useful equation is because, number one, it's like way easier to use than the conservation of kinetic energy equation. But also, that equation tells us something really important conceptually. What is v1 minus v2? Think about two objects traveling on some surface, like your table. If you take v1 minus v2, what is that? It's the relative velocity. And so notice what that equation says is the relative velocities are equal and opposite. before and after the collision. And that is a really, really, really important conceptual piece of information. Now, before we write down some big note here, I'd like you to take a second to pause this video and make sure you have all this written down. And when you hit play, we'll move on. So, huge note. This means the relative velocity, how much faster one is going compared to the other before the collision, is equal and opposite to the relative velocity of the objects after the collision. Huge conceptual point here. Take a second to pause this video and write that down. And when you hit play, we'll move on. So just to make it perfectly clear here, what we have done allows us to now say for an elastic collision, these are the relevant equations. And this is what we need to solve simultaneously. And I'll write that down here. Solve simultaneously. And this, I would hope you would agree, is much easier to solve simultaneously than these equations in their pure form. Take a second to pause this video here and write that down. And when you hit play, we'll actually go ahead and take a look at an example. Let's take a look at a problem. This problem here says a ball of mass 0.440 kilograms moving east, so in the positive x direction, with a speed of 3.30 meters per second collides head-on with a 0.220 kilogram ball at rest. If the collision is perfectly elastic, what will be the speed and direction of each ball after the collision? Now, it should be noted here, even just before we start this, that this phrase here at the very end of the question, what will be the speed and direction of each ball, particularly that they ask here for each, tells you that there are two unknowns. And the fact that there are two unknowns means you have to solve two equations or use two equations in order to be able to fully answer the question, right? Because you can't use one equation to solve for two unknowns. It doesn't work like that, right? So it's important to realize that there will potentially be some problems where you have a perfectly elastic collision where you'll only have to solve for one variable. And if that's the case, then you could use either of the equations that we developed. However, if they ask you for the speed and direction, in other words, the velocity of each ball, then you have to use two equations. And so that's what we're going to do here. So the first thing we do, obviously, whenever we're solving one of these problems is to just make our list of notes. And so that's what we'll do here first. I always, and you can really do what you want here, but I suggest you follow my advice to make it easy when you're looking at homework solution sheets. Whatever object they list first, for me, that's M1. So that ball of mass 0.440 kilograms, that's what I'm going to call M1, only because it is listed first. So that ball 0.440 kilograms. They tell us here that its initial velocity is 3.30 meters per second. They tell us here the other object now, it collides head-on with an object with a mass of 0.220 kilograms, and that object is initially at rest. So it has a velocity of 0 meters per second. And we're asked to solve for the final velocity of both balls. So that would be v1 prime and v2 prime. And that's it. We're ready to go. Now, the first thing you should do here is use the kinetic energy equation, because that's the equation that has no mass. Ultimately, you're going to take the result of that equation and plug it into the conservation of momentum equation. So just to go back to it, you usually start with this equation. You solve it for one of the velocities, and then you take that and you plug it in to the conservation of momentum equation. So that's what we're going to do first. So we have v1 minus v2 equals the negative of v1 prime minus v2 prime. And here, this I decided to do for our first example. This one's a little easier because v2 is 0. So that means here we have v1 equals negative v1 prime minus v2 prime. And you could really do this whichever way you'd like. It doesn't really matter. But the first thing you have to do is distribute. this negative sign. That's a really crucial step, because if you don't do that, then your signs are going to be wrong for the whole thing. So really, when we distribute this negative sign, we have negative v1 prime plus v2 prime. And really, for no other reason than pure laziness, this v2 is already positive, so I'm going to just leave this. I'm going to add v1 prime to the other side, and I'm just going to solve this for v2 prime. So I have v2 prime equals v1 plus v1 prime. Now, you could leave this like this symbolically, or you could plug in the numbers. It doesn't really matter. We can just go ahead and solve this for v2 prime and leave it like that. And now what you have to do is you have to take that result and you have to plug it in to the conservation of momentum equation. So we start by writing the conservation of momentum equation. m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. And of course, because the initial velocity of the second object is 0, that goes to 0. So we have m1v1 equals m1v1 prime plus m2v2 prime. And now is where we plug in for v2 prime this result here. And so we have m1v1 equals m1v1 prime plus m2 times v1 plus v1 prime. It's important to realize the reason we have to do this step is because now notice the only variable in this equation that we do not know is v1 prime. We have m1, which we know, v1, which we know, there's m1 again, m2, which we know, and v1, which we know. And so the first move we have to do here now, rewriting these terms out here in the beginning, is we have to distribute that m2 to both terms. Now, this is the part that usually looks a little messed up because we have m2 v1. And usually, I think, at least for me, when I get into the habit of writing conservation of momentum equations, I'm just doing m1 v1, m2 v2, m1 v1, m2, and the ones and twos go together. But here, once you make that substitution, it doesn't go together like that with the subscripts. So really, the name of the game here is just being really careful. And honestly, I like to just take a brief moment to stop and just proofread every line and make sure I've transcribed everything correctly before I move on, because this is a kind of problem where any little mistake like that will just absolutely kill you, because then the whole thing is wrong and you've done all this work now and you have a mistake. So all I'm going to do here really on the next slide is just rewrite that line here. So I have m1 v1 equals m1 v1 prime plus, and then notice here I just have m2 v1 and then m2 v1 prime. And so the key point here is now we're solving this for v1 prime. So at the very least, I've got to gather the v1 prime terms on one side of the equation, because notice it appears in more than one term. So I have m1 v1, I got to subtract over m2 v1, and then that's equal to m1 v1 prime plus m2 v1 prime. And so here, this is pretty simple. I have m1 v1 minus m2 v1, and notice that actually has v1 in there in both parts, so I can factor that out. I'll do that on the next line. And then I have a v1 prime times m1 plus m2. And so to solve this for v1 prime, I'm going to factor out that v1 here. So I have v1 times m1 minus m2, and then that's over just this sum of the masses here, m1 plus m2. And so I have v1 prime, which remember was what we're looking for, times v1, and that's 3.30 meters per second, times the difference in the masses. So m1 was 0.440 kilograms, and then we're going to subtract that by 0.220 kilograms, and then we're just going to divide that by the sum of the masses, 0.440 kilograms plus 0.220 kilograms. And when we do that math, you end up getting 1.1 meters per second for v1 prime. Now that's a lot of work to get v1 prime. And notice we still have to solve for v2 prime. But now all we have to do, we've set ourselves up quite nicely, is use this equation that we wrote for v2 prime here in the beginning of all this, and we have our v2 prime. So v2 prime, we already said, is equal to v1 plus v1 prime. And so that means v2 prime is going to be V1, 3.30 meters per second, plus 1.1 meter per second, and that gives us a V2 prime of 4.40 meters per second. And that's it. Now, I know it sounds silly to say, and that's it for a problem that's that long, but I think once you sort of do some examples of this and get the hang of it, you'll realize that most of this is just algebra. And since a lot of this was just algebra, I want to take a brief moment to return to the physics. There are two physical principles that must be obeyed here in order for this problem to be correct. The first was this point here. The relative velocities have to be equal and opposite. So in other words, however much faster one is going than the other has to be the same but negative. And so really, if one is going X amount faster than 2, then that means at the end, 2 is going to be going X amount faster than 1. That's a pretty good check to do at the end, just to make sure you haven't screwed anything up. So looking at the knowns here, we can see in the beginning, V1 is 3.3 and V2 is 0. So that means 1 is going 3.3 meters per second faster than 2. And if we look at the end, 2 is going 4.4 meters per second, and object 1 is going 1.1 meters per second. And notice now object 2 is going 3.3 meters per second faster than object 1. That gives us a pretty good indication that we've answered the question correctly, because the fact that that equation is true, that in the beginning 1 is going 3.3 faster than the other, and at the end 2 is going 3.3 faster than 1, that tells us the kinetic energy is conserved. And it's not a perfectly elastic collision unless the kinetic energy is conserved. The last thing we can say here is we can now calculate the change in momentum, or the impulse, experienced by each object. And if those numbers are the same, then we know for a fact that we've done this problem perfectly correct. Now, of course, you don't actually have to show the work for this, but since it takes like 2 seconds to do in the calculator, I don't think it's a bad idea to check, because you don't want to do all that work and end up having the thing wrong. Now, I'm not going to go ahead and write knowns and unknowns here just because this problem was long enough already. But just as a quick check, we have J equals M delta V. Notice here now, instead of writing final and initial, I've written V1 prime minus V1. And so M1, I'll write M1 there, is 0.440 kilograms. Remember, V1 prime was 1.1 meters per second. And the V1 value was 3.30 meters per second. And when you do that math, 1.1 minus 3.30 and then multiply it by 0.440, you get negative 0.968 kilogram meters per second. That makes sense because object 1 was moving to the right and crashed into object 2, which was stationary. That means object 1 experienced a force in the opposite direction of its velocity, which made it slow down. It did, in fact, slow down. It had a force act opposite the direction, which decreased its momentum. Okay, cool. Now, for object 2 had an equal and opposite force, meaning that force was to the right. And since that object started from rest, it gained momentum. And so the impulse here should be positive. And so we have here J equals M2 times V2 prime minus V2, M delta V, the change in momentum. And we had the mass here for object 2, which was 0.220 kilograms. And we're going to multiply that by V2 prime, which we calculated, remember, as 4.40 meters per second, minus V2, which, easy enough, was 0. And so when we do that math, we get, what do you know, 0.968 kilogram meters per second. The impulses are equal and opposite. The velocities, relative velocities, are equal and opposite. So the momentum and the kinetic energy are conserved. Now, obviously, I want you to solve one more example of these and to do it on your own. But since this video is already way too long as it is, with that, that's it for today. We'll take a look at a couple of these examples tomorrow. Have a good one, everybody.